Hi there. One way for a beginner to buy a decent multimeter for not too much money is to target the market for used meters. Here I have such a thing, a Fluke 25 from eBay. Now for Flukes, even very old models cost easily more than new meters from less known brands, like for example the one you see next to it. You pay for the Fluke name and reputation, build quality, safety and so on. So to get an affordable Fluke, you may have to take your chances with something sold for spares or repair, like this one. So how does this one do? Well, the display works, which is good, but no sensible DC volts. And it's the same for DC millivolts. But interestingly, like before, there is an initial value that then fades to zero. The first really good news, DC milliamps seems to work just fine. That means the basic circuits in this meter are okay and there's a good chance to fix it. AC microamps is working also pretty well, and so does milliamps, which I didn't show, and also amps for both DC and AC work as well. AC volts shows something but not the right value, and AC millivolts also shows some value which is not correct, but at least it's not zero. Here's a look at a part of the Fluke 25 schematic from the service manual, which you can download from the Fluke website. Now don't get me wrong, I really appreciate the fact that Fluke makes this available, but I really wish they had spent a bit more care in scanning it, because it's pretty horribly put together with pages out of order. It's also missing essential parts, like what these switch settings correspond to. After a long search, I finally found an online Fluke 27 manual that somebody has restored, which includes that info. The Fluke 25 and 27 are almost identical, so that helped. Anyway, the fact that DC volts shows something initially and then fades to zero, and AC volts shows something but with the wrong value, made me wonder if the problem is a capacitor that is accidentally left in series when measuring DC. That would be this capacitor C3. It is used to block DC when measuring AC volts. When DC volts is selected, the capacitor is shortened by contacts 11 and 12F. If that shortening doesn't happen, it could explain the strange DC volt behavior. DC current ranges use a different path, so those may well be working and DC volts not. But ohms relies on the same contacts to have C3 shortened. To test this, I used a slow triangular wave, so the voltage is always changing, and indeed, it looks as if a tiny bit gets through in DC volts. And ohms definitely does not work at all. I think that's all I can deduce from the outside. Time to open the meter up. This, by the way, is a military version in dark olive instead of the Fluke yellow. It also misses the tilting bale, but that would be the least of the problems. Regardless of military or civilian, the Fluke 2X series are built like tanks and built to military shock, vibration and water resistance standards. With the battery compartment open, the 9-volt battery is accessible as well as the fuses. There are 4 additional screws that hold the rear housing. 2 of these are only accessible through the battery compartment. The screws have seals to ensure the water resistance, but I would not rely on this after all these years. Lifting the rear does not give us great insights. A big shield is all that's visible, but on the side are many trim pots or trim capacitors, so calibration can be done without disassembling further, which is nice. The service manual says to make sure the function switch is in the upper off position before taking it further apart. That begins with opening the 4 screws that connect the terminal sockets to the PCB. It is refreshing to see such a solid construction compared to the flimsy sockets we get nowadays. With these disconnected, one is supposed to carefully pull the upper part away from the lower one, because this effectively is a PCB sandwich and the lower part with the display stays in the housing. This is much easier said, or rather written in the service manual, than done in reality. I really struggled on this because I did not want to break anything. Well, I finally succeeded and the 2 halves separated. The lower part is just a processor, display and beeper. All the analog magic is happening in the other part, which is completely enclosed in shielding. The mechanics of the function selector with its springs and indents looks like new, still greased after all these years. This was really built to last. The shaft of the selector extends to the analog part, and they have made a helpful print on the shielding Interestingly, the setting is in the upper off position, yet the blue part appears slightly turned, but this is also the way the service manual shows it, so all is fine here. Not so fine is the board-to-board connector. It is kind of difficult to see, but the fourth pin from the bottom is horribly bent. That must have happened when someone assembled the two halves without properly aligning all the pins. Is a bent pin that makes no contact the cause of all the problems this meter has? For clarity, I'm using the Fluke 27 schematics here, but as you can see, pin 3 and 4 only connect to the beeper. I did not test continuity because ohms didn't work anyway, but clearly with the pin bent, the continuity beeper would not have worked. A quick note, the only real difference between Fluke 25 and 27 is that 27 has these two additional buttons for rel and max min. Apart from this, the specs are identical, and I would say that chances are good if one would add those two buttons cleanly, you could upgrade a Fluke 25 to a 27. Anyway, the disassembling continues by opening 3 screws on the top of the shielding, and then removing 4 more on the other side. Apologies for the lighting, this shield reflects light like a mirror. Finally, the underside of the PCB with a big Fluke branded chip and some nice cutouts. And there is the other side with most of the components. You can see the mangled pin of the connector a bit better with the shield gone. It looks very well built and very clean for being 40 years old. The capacitor I was suspecting being left in circuit is this one here. 22 nanofarad rated 1000 volts. The switch contacts that short in DC volts are these two, so this is an easy test. If the function switch is off, the cap is not shortened and my primary meter reads about 22 nanofarad. Turning the switch to DC volts and the capacitance readout disappears and reappears when turning the switch back. Okay, fine, but better check whether it's really shortened by switching the primer to show ohms instead. In the off position where it previously showed 22 nanofarad, it now shows infinity ohms, and turning it to DC volts shows close to 0. So my theory was wrong, the cap and the switch work just fine, and the problem is elsewhere. The service manual actually has some fault finding hints, and for a problem with DC volts, and as the first step it suggests to select the DC volt function and apply 2 volts on the input terminal and then check if 2 volts appear on pin 1 of the resistance divider network Z1. Now Z1 is shown here, but confusingly that's only part of it, and the pin 1 of Z1 is actually right here. Let's do that then. 2 volts are on the input terminal, but only about 12.5 millivolts appear on pin 1 of Z1. Clearly, the problem is in the path from the terminal to Z1. The only thing that could cause this is R2, a 1K resistor. It is marked in the schematics as 1K 2 watt wire wound 10% tolerance. Checking the parts list reveals that this is a 2 watt fusible resistor. In other words, it acts like a fuse in severe overload conditions. It also states that it's of type MF, that is metal film, and a 1% tolerance part. Fluke, make up your mind. The same service manual specifies it as either wire wound 10% or metal film 1%. Checking the resistance of the 1K resistor shows infinity, so yes, it is blown. By the way, that blown resistor probably now acts like a small capacitor in series with the input, letting some part of AC through, so my initial theory wasn't completely wrong. I could not find the Fluke part, and searches for fusible 1K 2 watt resistors turned out basically one choice, the Vishay PR02 series. It is metal film, so it meets the parts list but not the schematics, and the only tolerance I could get was 5%, which is better than the 10% of the schematic but worse than the 1% of the parts list. Regarding the fusible part, the datasheet did not contain data for a 1K PR02. The best I could find is this graph for PR02 up to 560 ohms. According to this, loading it with 40 watts will rupture it between slightly more than 1 second to a maximum of 10 seconds. 50 watts should do it from 1 second to 8 seconds. Since I could not get the 1% part, I bought 40 of the things and measured every one to find one with the closest tolerance, which is the one I'm showing here, which is just 6.2 ohms lower than 1K, which translates to 0.62%. Interestingly, all 40 were actually pretty good. Most were within 1% and none exceeded 1.2%. You may have noticed that this shows only 39 resistors. That's because I picked one to be sacrificed to test its fusibility. According to the datasheet, I need at least 40 watts. To get that kind of load on a 1K resistor is not that easy, and I basically had to use mains voltage, so my variac set to a more or less constant 200 volts. The blue meter shows the voltage and the red one records the current every half second. On with the fireworks! Not that spectacular, but then these are flame resistant and whatnot. They still leave quite a stink. You definitely notice that some magic smoke has been released. Here's the recording. The load started with a predicted 40 watts and quickly peaked at just about 55 watts. As the resistor was just about to burn through, the resistance dropped and therefore the current and watts increased. The whole thing was basically over in slightly more than 5 seconds. The resistor is now infinite ohms, just like the one in the Fluke 25. Although blown, the resistor does not look all that bad. If you didn't know, you would probably not suspect that something bad has happened to this one. Only by direct comparing it with a new one do you notice that the color rings have lost their shine and the red ring has turned black. I replaced the bad one in the meter with my hand-picked PR02 fusible resistor. It is strange that it looks quite a bit smaller than the old one, but the resistor is rated for 2 watts as the manual says. The color bands on the original one make no sense, and I have read the same comment from other people repairing fusible resistors on Fluke 25s. There's absolutely no trace of any burn mark on the body or on the PCB where it was mounted, but as we have seen, those are sometimes not easy to spot on fusible resistors. Still, one wonders if this resistor has not failed because of old age rather than overload. I used some pliers to gently bend pin 4 back to be reasonably straight without breaking it. Still, I spent at least 10 minutes when putting the meter back together trying to ensure all pins were aligned. This is incredibly difficult because the shielding makes it very hard to see. The big question, is it working? Yes, success, we have DC volts back. Not only that, it's very accurate. And AC volts? Works too, of course, and also very accurate. I tested here with a sine wave because the Fluke 25 is showing average voltage calibrated to RMS, not true RMS. And resistance is working as well, and accurately, no complaints. Continuity is going to show if my pin straightening and careful connector alignment worked. Yes, we got a beep. And how about diodes? It does the Fluke typical short beep if the forward voltage is in the right ballpark for standard diodes. It can light a red LED and display the forward voltage, but no beep in this case. Now that I have a functional meter, some more notes. First of all, forget standard probe leads with shrouded safety plugs. The Fluke 25 can't accept these. Instead, you have to use leads with standard 4mm non-shrouded banana plugs. These are available, or you can trim the shrouds away with a knife. The Fluke 25 has the fabled Fluke touch hold. If turned on, the meter will capture stable reading and then automatically holds it. The display is automatically updated if you do another stable reading. This is quite a nice feature and works well, especially for tricky measurements where you need to concentrate on probing rather than looking at the display. Nominally, the highest resistance the Fluke 25 can measure is about 32 megohm, so it shows OL when trying 100 megohm, but it has a nano-Siemens mode. You have to use the manual range to get to it. About 10 nano-Siemens, which is equivalent to about 100 megohm, no problem. I always test the current consumption of multimeters to get an idea about battery life. The red meter shows the voltage at the Fluke's battery terminals and the blue meter the current from my bench power supply. Only about 330 microamps at 9 volts, which is an excellent value. This means the 9-volt battery should last an eternity. And even the beeper needs just a modest 1.5 milliamps. I tried to measure when the low battery indicator comes on, but to my surprise it did not. Right down to 4.4 volts when the Fluke 25 started to show errors in the measurements, and at 3.55 volts when it finally shut down. It turns out that the low battery is only tested on startup or when the function switch is moved, which is fair enough. Hence, it shows a low bat when starting at about 5.5 volt battery voltage and has no problem at 6.5 volts. Regardless whether the indicator comes on at 6 volts or 5.5 volts, these are excellent values which make the Fluke 25 well suited for use with rechargeable 9 volt batteries, which mostly have a nominal voltage about 8 or even just 7.2 volts. Okay, so a Fluke 25 will last a very long time on batteries, but is it worth having a Fluke 25 these days? Let's check the specs. The values are quite impressive. In terms of accuracy, the Fluke 25 or 27 runs rings around the recently reviewed More Pilot 17B or the Grenova in all ranges and functions. But there is a particular feature that I want to highlight. Look at the AC volts frequency range. The spec goes to 30 kHz, making this one of the very rare multimeters you can actually use in audio applications. Okay, current ranges are a bit more pedestrian, but that is expected. I tested the accuracy of all ranges and I can confirm that the meter still meets or exceeds these. Of particular interest for me was the AC bandwidth, and here the Fluke 25 does not disappoint. Although only specified for 30 kHz, it goes on and on to almost 100 kHz. Then we have some kind of resonance bump before it finally hits the -3 dB threshold at 250 kHz. When I said earlier that the meter still meets its spec, for AC I did that test at 100 Hz, like you see here. It turns out that it was a little bit off at higher frequencies. That is where all these trimmers come in. There's a detailed cal procedure in the service manual that calls for 2.7 volts, 27 volts, 270 volts and 1000 volts, all at 10 kHz to adjust them. Well, it turned out that with my equipment I can't produce 1000 volts at 10 kHz, so I skipped that, but 270 volts is doable. Okay, not exactly 270 volts, but close enough. I only need to adjust the Fluke 25 to read the same value as shown on the Agilent. Sorry, I adjusted the generator without showing it on camera and the value was now 272.3. The Fluke is just a little bit low. It turned out that those trimmers have really deep recessed screws and I found it very difficult to get any purchase with the trim tools I have. Although this one has just a tiny metal plate in an otherwise plastic body, it disturbed the reading, so when the tool was removed, the reading changed. This means you basically have to adjust on a try and error basis, which is very time consuming. Anyway, at the end with 272.2, I called it good enough. I won't bore you with the same adjustments on the other ranges. After that job, I decided to rerun the bandwidth test to see if it made any difference. The new curve is the red one, while the blue one is the original before I calibrated. The bump at the end got a bit larger, but those frequencies are anyway outside the valid measuring range. More importantly, the calibration flattened the frequency range from 1000 Hz to 60,000 Hz somewhat. I know the difference wasn't a lot, just 0.2 dB to begin with, but now it's considerably less, which is great. Finally, I mentioned that the Fluke 25 and 27 are practically identical and the 27 just has the additional rel and max-min buttons. But interestingly, there are some other differences. It looks as if Fluke improved the input protection for the 27. Where the Fluke 25 has a fusible resistor I just replaced, the Fluke 27 has a combination of a 3.5K normal resistor in series with a PTC, which is certainly an improvement. Also for the current, the Fluke 25 has 3 fuses, a 15 amps for the 10 amp range and strangely a 3 amp fuse in series with a 630 milliamp fuse for the milliamp range. Obviously they didn't trust the tiny 630 milliamp fuse to provide sufficient braking capability. The Fluke 27 has just 2 fuses, both of the large kind. The amp fuse is now rated 11 amps instead of 15 and the milliamp range uses a 440 milliamp fuse. The point of all this, if you have a choice between the Fluke 25 and a Fluke 27, maybe the 27 is the better option, not just because of the additional buttons. It is always risky buying multimeters on eBay, especially if they need repair. If you consider trying it, older Flukes are a good candidate because their service and calibration manuals are freely available. Also, those old Flukes have a reputation of staying in calibration practically forever as long as the previous owner did not mess them up during failed repairs. This Fluke is now fully working and back to be a very usable multimeter. If you like my videos, don't forget to subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.